At the beginning of 2020, the Las Vegas High Roller was the world's largest observation wheel, which is the fancy word for Ferris wheel. This YouTube video provides a brief and fascinating interview with the wheel's architect, and I highly recommend you check it out. The High Roller measures 550 feet in diameter and completes one full revolution in 30 minutes. This is slow enough that riders may board the wheel by entering a cabin as it moves along the loading platform. The wheel does not stop. Each cabin holds 40 people. Now, just to get an idea of the scale of this thing, what is the High Roller's diameter in miles? It's a meaningful calculation. We'll take 550 feet and we know that there are 5,280 feet in a mile. So yeah, this is 0.104 miles in diameter. Really big. Now, suppose you board a cabin on the High Roller when it is closest to the ground, exactly the same height as the boarding platform. You stay on the High Roller for 1 hour. And remember, we make a full revolution within 30 minutes. So let's complete the table below. I want to plot the time versus the height. So height above the boarding platform, not height off the ground. We're just going to keep it simple and say the height above where you step on. So when time is 0, we are at the boarding platform. Height above the boarding platform is 0. We've got 7.5 minutes. That seems more challenging. Let's skip it. When we get to 30 minutes, that's one full revolution of the wheel. So that also would have 0 height. That would mean we would come all the way back around to the boarding platform, which means that 15 minutes must correspond to our maximum height. Now, if we think about the shape of the wheel and the boarding platform, there's where we are when we're at the very top of the wheel. That means that our height would be the diameter. So at 15 minutes, we should be 550 feet up. So the further implication then is that at 7.5 minutes, we should be at half that height. So we would say that that is 275. And at 22.5 minutes, we are making our way back down at that stage. We'll have gone from the top and made our way down to there. That would be 22.5. So that should be 275 again. 30 minutes takes us back to start. So then 37.5 minutes. Well, 37.5 minutes would be from start half the way up. So that should be 275. 45 would be again 550. 52.5 back to 275. And finally, 60 minutes, we're back at the boarding platform. Now, using the table, I want us to create a graph plotting height versus time. So we do know what the graph represents. Knowing what the graph represents, should you connect the dots? If so, how? Let's come back to that after we get the dots onto a graph. Okay, so We know that our x-axis is time in minutes, and we know that our y-axis is height above the boarding platform in feet. So 0, 0. There's a start point. Let's go ahead and take our y-axis and chop it up in those 275 unit blocks. We know we're going all the way up to 550, and so then we're going to have 275 right about there. On the other axis, we are going out to 60 minutes. We also have a touch point at 30 minutes, and from there we can keep subdividing. 15, 45, and there's our 7.5, our 22.5, 37.5, 52.5. Start plugging in points. At 7.5 we were at 275, so there will be that point. At 15 we were all the way up to the top, so that put us at 550. By 22.5 we were back down, but not until 30 were we all the way at the bottom. And then we started moving up again. Okay, so when we plot the points like this, it is acutely tempting to say, okay, should we connect the dots? Well, yeah, we should connect the dots. They're definitely, I mean, the Ferris wheel is moving the whole time, right? So, I mean, this point right there, like there's gonna be some height. We don't know exactly what it is, but we know that it's there. So that seems to make it reasonable to connect my dots. But wait, how? How do we connect the dots? There are a couple different ways we could connect these dots, right? We could go make it real spiky and quick change, like, I mean, I'm connecting the dots. But this doesn't quite accurately reflect what's going on either, because if we were to plot more points, we would see a different behavior. This graph is plotting the height versus time. Now, our height changes very rapidly vertically, right? This vertical motion very rapidly right around 7.5 minutes. That's where the car is going almost straight up and down, as courtesy of the rotation. But it changes quite slowly at the very top and at the very bottom. You think about that time where you're boarding the car, it's kind of moving almost, if you looked at that video, you see the car moving almost completely horizontally to appearances because the wheel's so big. Not really doesn't look like it's moving up and down, and that's a tell. That tells us that height doesn't change a whole lot until you get to those middle points. So we should be connecting them smoothly. Let's see if I can do a better job of that. Yeah, we'll take it. Periodicals. I'm now going to assault you with more definitions than any packet should have on one page. But happily, they refer back to the previous page, and they're just mathematical names for ideas that you already know. Here we go. Definition. A function f of x is periodic if its values repeat at regular intervals with respect to x. So how often does your graph of height on the roller coaster repeat itself? Let's go back and take a look. We were at 0, and then we did through, and we got back to 0 at 30 minutes. And we went up again, we went up all the way up, and we're back again at 60 minutes. Okay, so we're repeating every 30 minutes. 30-minute interval. The fancy mathematical word for that is the period. The period of a periodic function is the frequency with which the function values repeat. So if you look at our graph, we get the same value every 30 minutes. Thus, the period of the high roller is 30. Next definition, the midline of a periodic function is the horizontal line halfway between the function's minimum and maximum values. So in our case, the minimum was 0, the maximum was 550. Go back and add a dotted midline for your graph of the height on the high roller. Okay, so 550 is the top, 0 is the bottom. Yeah, 275 is right in the middle. So midline would be h equals 275. Next up, amplitude. The amplitude of a periodic function is the distance from the midline to the maximum or minimum values of the function. And let's highlight this. Or, it's not the total spread. So, not total spread between max and min. Rather, it's the distance from the midline. So, what is the amplitude of the graph that we made for the high roller? Well, again, let's go back and look at it. The max value is 550, the min value is 0. So, the midline being at 275, the amplitude is actually 275. It is specifically that right there. That is the amplitude. And it's equal to 275. Okay, one final thought. Hopefully you'll have more than one. If traveling on the high roller corresponds to a smoothly curved periodic function, oh, I'm skipping the amplitude question. What is the amplitude of our graph? Our amplitude was 275. Okay, but back to this. If traveling on the high roller corresponds to a smoothly curved periodic function, what is a real-life experience where minimum and maximum values of the corresponding periodic function are not connected smoothly? How many such examples can you find? Take some time, think about this. You could poke around on the internet. Fair game. If you can come up with them yourself, that's great. But do come to class ready to discuss. We'll be doing some small group breakout around this.